The topic of this screencast is quantum models of the atom. Recall that, although Bohr's model accounted for hydrogen's emission spectrum, it still had two problems. And remember that Albert Einstein proposed that light could be described as photons of energy. In other words, energy could be like a particle. Taking a page out of Einstein's book, de Broglie hypothesized that particles, including electrons, could be like waves. According to de Broglie, electrons can only orbit the nucleus in complete waves, that is, whole numbers of wavelengths. The results of his experiments led de Broglie to derive the following equation. In addition to velocity, which can be measured for waves as well as particles, the equation includes the wave-like variable wavelength. In addition, it incorporates two particle-like variables, mass and Planck's constant. The de Broglie equation therefore allows us to assign a wavelength to any moving particle. In short, particles can be like waves. Note that mass appears in the denominator. This means that, as mass increases, wavelength decreases. For example, a car moving at 25 meters per second with a mass of 910 kilograms has a wavelength of 2.9 times 10 to the negative 38th meter. This wavelength is far too small to be detectable. Conversely, as mass decreases, wavelength increases. So, an electron moving at the same speed as the car would have a wavelength of 2.9 times 10 to the negative 5th meter. This wavelength is definitely large enough to be detected. Visible objects like these have wavelengths that are far too small to be measured. Which of these items, baseball, human, car, or planet, has the shortest wavelength? If you said planet, you are correct. Objects that are not visible to the naked eye, like these, have wavelengths that are large enough to be measured. Which of these items, atom, nucleus, proton, quark, or electron, has the longest wavelength? If you said electron, you are correct. Therefore, electrons with a mass of virtually zero are in fact waves of electromagnetic radiation moving at nearly the speed of light. They are not particles, and therefore they cannot crash into the nucleus. This is a whole new set of rules for particle motion. The laws of motion set down by Newton simply do not apply. Electrons are playing by a new set of rules. That set of rules is known as quantum mechanics. So while classical mechanics correctly predicts the behavior of visible objects moving at ordinary speeds, quantum mechanics must be used to predict the behavior of very small objects moving at nearly the speed of light. One of the new rules of quantum mechanics is known as the Heisenberg uncertainty principle. Heisenberg showed that it is impossible to take any measurement of an object without disturbing it. The Heisenberg uncertainty principle states that it is impossible to know exactly both the velocity and the position of a particle at the same time. This principle does not apply to visible objects such as airplanes. Why not? Suppose you want to find a balloon in a dark room. You need to turn on the light to see it. Einstein tells us that the beams of light are composed of tiny massless packets of energy known as photons. The photons strike the balloon and reflect back to our eyes, revealing the balloon's position. Because of the balloon's size, the effect of the rebounding photons on the balloon's position is far too small to be observed. That is not the case for electrons. When we attempt to determine an electron's position, any photon colliding with the electron will excite it, causing it to move to a higher energy level and also altering its velocity. As a result, it is impossible to measure an electron's velocity and location simultaneously. The best we can do is to state the likelihood of finding an electron in a particular region around the nucleus. Solving Schrödinger's wave equation gives us these most probable regions around a nucleus where electrons can be found. The wave equation allows us to picture the arrangement of an atom's electrons according to the quantum mechanics model. The equation does this by allowing us to determine the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus. The wave equation predicts that electrons are most likely to be found in three-dimensional regions around the nucleus. These regions are known as orbitals, and they are very different from orbits. We picture orbitals like fuzzy clouds. An electron can be found within an orbital 99% of the time. However, it is moving at nearly the speed of light, so it would appear to be everywhere in that orbital at the same time, hence the fuzzy cloud. Thus, we say that electrons are found in the atom's electron cloud. By the way, we use the wave-like properties of beams of electrons to magnify teeny tiny little objects like viruses. The electrons in an electron microscope have much smaller wavelengths than visible light. So, they are able to reveal incredible detail of really small objects, such as the face of this mite. Now, let's suppose you are an electron in the FHS atom. What does your electron cloud look like? And how would your electron cloud change when you are excited by heat or electricity? We will consider these questions together in class. Until then, thanks for watching.